Okay, I'd like to talk very, very quickly about section 11.2 and maybe 11.3. Okay, so more 11.2 and 11.3 from the textbook. I want to think about one specific series. This is called the harmonic series. It's the series that starts at 1, and so it's called the harmonic series. It's a series that starts at 1, and we add a half, and we add a third, and we add a quarter, and so on. And I wonder whether or not this converges. Well, I don't wonder. I know that it doesn't converge. But that's a little bit shocking. You might expect that it converges. So here's a picture that will convince you that indeed it diverges. So this is going to be the result. It diverges. Y. And here's the picture for y. All right, I'm going to start at 1. This is the graph of 1 over x, 2, 3, 4, and so on. Okay, this right here, I didn't draw it. I didn't draw it correctly, but this is a graph that has, or this is a box that should be a square. It has length 1, but then this coordinate right here is at height 1, right? Because the function is 1 over x, so you get 1 over 1, so that's 1. Right here, so this has area 1. This box here is 1 wide and it's a half high, so it has area a half. This box here is 1 wide and has area a third, and so on. If you think about this a little bit, then 1 plus a half plus a third plus a quarter plus up to plus 1 over n. This is going to be bigger than the integral from 1 to n plus 1 of 1 over x. Right? Why do I say that this will be bigger than this? Because these sums will be the sums of these rectangular boxes, and they're all higher than the graph. So this will represent the area of the graph, this will represent the areas of these boxes, and the area under the graph will be smaller. Okay. Now if you take a look at what this is the natural log of n plus 1. That's log of x, plug in that, and take the difference. So you get the natural log of n plus 1. This goes to infinity. Okay. The bigger n gets, the bigger this side gets. So there's no way that this could sum up to a finite number. Okay. So since this integral, as n gets larger and larger, becomes infinite, this sum will also get infinite. So there's no way that this converges. So this is a divergent series. This is one of the most important series that we'll talk about, and it's important to keep in mind that it diverges. So we take that, and we'll see what we can talk about with that later. Now there's a theorem that seems to contradict that result, but it doesn't. So it says that if you have a series, we'll start at 1, it doesn't matter, is convergent. So if you have a series that's convergent, then it's necessary for the terms of the series to go to 0. Okay. Here's another way to say this. Another way to say this is if the terms of your series don't go to 0. Okay. So that means if the limit of the ands is not 0, or if it does not exist. Okay, so this is if the limit isn't 0, then this series diverges. Okay, so these two statements are logically equivalent. If you have a series for which the terms don't go to 0, then the series diverges. Or if the series is convergent, then the terms have to go to 0. So this seems to be contrary to the previous example, but in fact it's not, because the series, the harmonic series that we saw in the previous thing, was not convergent. So it didn't satisfy this part of the statement, so this part is meaningless. Anyway, it's an important logical distinction to keep in mind. But let me show you an example of where this helps us a little bit. So here's, how about 5n squared over n squared plus 4. We'll just start from 1 to infinity. Okay, so this looks like 5 over 5 plus 20 over 8 plus 45 over 13 plus, and then it goes on and on and on. But take a look at what's happening with these terms here. What is the limit of these terms? 5n squared over n squared plus 4. This is going to 5 as n goes to infinity, right? Because 5n squared here, n squared in the bottom, the two leading powers of, the two coefficients of the two leading powers, their ratio is 5. So, so this will limit to 5. So that means that after a long time, you're going to be adding something that's approximately 5, and then you're going to be adding something else that's approximately 5, and then you're going to be adding something else that's approximately 5, and you're just going to keep doing this forever, okay? How could that possibly converge, right? It can't, right? Because you just keep adding more and more things that are closer and closer to 5. But this is why. So we're using this aspect of the criterion here. If the limit of the terms of the sequence isn't 0, so in this case here it's not 0, right? It's 5, then this has to diverge. So this diverges according to this theorem. Okay. We'll use that all the time. Okay. Finally, some laws. So if a n is a series and b n is another series, both converge, then the following are true. So then this an plus bn converges, and it converges to whatever these things are. In fact, it's true if you replace that with a minus. So if you subtract two series from each other, then you get this. So that's one law here. If you take if you have c, if c is any constant, so this just means c is a real number, then the series of c multiplied by the ands, this converges, and it converges to that. Maybe as an example, we could take a look at, so let's just take a look at this example. I'll start at 0. How about 3/4 to the n minus 7 over 2 to the n? This series right here. Okay, we know that 3/4 to the n is a geometric series, and 7 over 2n is also a geometric series. So we can sum this by doing the following. We can split 3/4 n minus, and then I'm just going to bring that 7 out, 1 over 2 to the n, like this. And so we've used both of these laws. We took 7 over 2 to the n, that's using this constant, pulling constants out rule, and then we split this along a difference, and we can do that as well. So if you recall what the formula was for these, then it looks like 1 over 1 minus 3/4, and then this is 1 over 1 minus a half. So whatever that works out to be, this will be the sum of this series right here. As long as we're continuing to make progress here, let's go forward with 11.3. This is about something called the integral test. We're not going to spend much time with the integral test, but we will use the integral test for a fundamental result. So what the integral test says is it says that if, so this is the theorem, if f is a positive, I don't know why I wrote positive there, positive decreasing function on, let's say, 1 to infinity, and so that's f of x. And if an is equal to f of n, then the series a of n converges or diverges, the police, exactly when the improper integral of f of x on 1 to infinity converges or diverges. So what this means exactly so that means that if this improper integral converges, then the series converges. And if this improper integral diverges, then the series diverges. So let's see this by an example. So I want to think about the following series. How about 1 over n squared? Starting at 1, going to infinity. So converges or diverges? Let's find out. So converges? Who knows? So we check. If we make f of x equal to 1 over x squared, then that means that if we plug in an integer, that's 1 over n squared, right? This is the an for our series right here. So it turns out, 1 over x squared, well, this is certainly positive, and it's decreasing on the interval from 1 to infinity. So we look at this integral here. Okay, so let me refresh your memory about improper integrals. Remember what this means. We let t go to infinity, we put a t up there, we put the 1 here, and we do 1 over x squared dx. So we measure the integral 1 over x squared from 1 to t, get that number, and then we see what happens when t gets larger and larger. So this is the limit as t goes to infinity of, let's see, the antiderivative of 1 over x squared is minus 1 over x. And then we're evaluating this from 1 to t. So we get, let's see, when we plug in t, we get minus 1 over t. There's a limit in here. Minus 1 over t, and then we get minus 1 over 1. So that's plugging in t and plugging in 1. When we take the difference here, this will turn out to flip the difference. So we get 1 minus 1 over t, like that. And as t goes to infinity, 1 over t goes to 0. So this goes to 1 minus 0. So this is 1. Okay, so good. So that means that the improper integral converges. Okay, therefore, the corresponding sum converges also. Okay. Now I want to make sure that you understand that 1 over n squared does not converge to 1. The improper integral converges to 1. But both of these things converge. They don't converge to the same number, but they converge. And that's all that we really care about, is whether or not this series converges. So it converges, but not to 1. That's not a part of the theorem. We don't actually know how to compute the sum of this using an improper integral. All it tells us is whether or not it converges or diverges. So let me give you an important consequence of this, which we'll probably talk about in class. So by the integral test, you can show the following fact, that the sum, n goes from 1 to infinity, 1 over n to the p power, to n raised to the p power, that this thing here converges whenever p is bigger than 1, and it diverges when p is less than 1 and positive. So that means, for example, 1 over n to the 4th, this series converges because 4, the power p, 4, is bigger than 1. So does n. Well, let's think about this. So 1 over n squared. That means that 1 over the square root of n diverges because the square root of n is n to the 1/2 power, and 1/2 here is less than 1. Okay, so anytime you see a series of the form 1 over n to a power, if the power is bigger than 1, then it converges. And that's true because you can show it using the integral test. And same thing is true, any power of n in the denominator that's less than 1 will cause the series to diverge, and that will also be by the integral test. So this is actually all I really want you to know from this section. This is section 11.3.